Welcome everyone. I welcome you to the second part of our video tutorials on analog electronics, PN Junction. I hope you must have gone through the first part of our video tutorials, which was on semiconductors. The link has been provided in the description below. PN junctions are a very important part of basic electronic circuits. They were created to replace the bulky vacuum tube diodes which used to consume lot of energy and used to dissipate a lot of energy as well. The size of these vacuum diodes produced a limitation in the size of the circuit that could be produced. PN junction diode, owing to their good characteristics, smaller size, low voltage requirements, was a game changer in the field of basic analog electronics. A PN junction can simply be defined as a metallurgical boundary in a semiconductor crystal in which holes are the majority carriers on one side, which will be the P type, and electrons are the majority carriers on the other side, which is the N type. It is also called as the PN junction diode. Now let's delve into the working and construction of a PN junction diode. The N-type semiconductor has free electrons as majority charge carriers. As it is electrically neutral, it has an equal number of donor ions. There are a few thermal holes present as well. The holes here are called the minority charge carriers. The electrons are the majority charge carriers and there are positive donor ions. The P side has hole as the majority charge carriers, thermal electron as the minority charge carriers, and negative acceptor ions. The negative acceptor ions are as same as the number of holes. Now let us join them. The methods to join them are grown junction diode method, alloying method, diffusion method, epitaxial growth method, and point contact diode method. The tutorial here will not cater to these different methods. You can go through different books and learn about these methods. I believe you will have a good experience. Coming back to our topic, due to the difference in concentration of electrons and holes on the two sides of the junction, the electrons in the N region tend to diffuse towards the P region and the holes in the P region do so towards the N region. This process is called as diffusion. The diffuse charge carriers combine at the junction to neutralize each other to form immobile positive ions in the N region and negative ions in the P region on both sides of the junction. This results in a charge-free region near the junction. As the region is depleted of the charge carriers, that is electrons and holes, this region is called as the depletion layer. The diffusion continues till the materials on both sides equalize their Fermi levels. An electric potential V0 is developed across the junction barrier. This potential is called the junction potential or the barrier potential. To summarize, the electrons and holes flow through both sides of the junction due to diffusion. A charge-free region is created, which is called the depletion layer, and it has a potential called the barrier potential or the junction potential. The symbol of a PN junction diode is as shown in the bottom left of the screen. The P is represented by an arrowhead and N is represented by a perpendicular line. When the PN junction is not biased, that is when no external potential is applied to it, the barrier potential does not allow the carriers to cross the junction. Hence, there is no current flow across the junction when it is at zero bias. Now, let's try to bias the diode. First, we will forward bias it. Now, what is forward bias? When the PN junction is connected in such a way that the positive terminal of the battery is connected to the P region and the negative terminal is connected to the N region, the PN junction is said to be forward biased. The free electrons from the negative terminal of the battery can now flow into the N region. At the same time, free electrons in the N region start moving towards the junction. As the electron travels through the N region as free electrons, current in the N region is due to free electrons. When these electrons reach the junction, they combine with the holes and break covalent bonds and valence electrons are formed. As the electrons traveling through the p region are valence electrons, the current in the p region is due to holes. When these valence electrons reach the end of the p side of the crystal, they flow into the positive terminal of the battery. The applied potential produces an electric field acting against the field due to the potential barrier. This results in weakening the electric field, and the barrier height and the width of the barrier is also reduced at the junction. As potential barrier voltage is very small, a small forward voltage can easily eliminate the barrier completely. This voltage is about 0.1 to 0.3 volts. Once the potential barrier is overcome, junction resistance becomes almost zero, and a low resistance path is established for the entire circuit. This results in a flow of holes and electrons across the barrier, or we can say that the flow of current is established through the junction. Let us summarize it. Connecting the positive terminal of a battery to the P side of PN junction and negative terminal to the N side is called the forward biasing. Forward biasing reduces the barrier potential and decreases the potential barrier's width. The current in the N side is due to the free electrons, and in the P side is due to holes. The current is only due to the majority charge carriers and is usually in milliamps. Now, let us connect the battery in the reverse manner. That is, we will connect the negative terminal of the battery to the P region and the positive terminal of the battery to the N region. The PN junction in this case is said to be reverse biased. Now, the applied reverse voltage will create an electric field acting in the same direction as the field due to the potential barrier. This will strengthen the electric field and the barrier height will increase. The width of the depletion layer will also increase. This increased potential barrier does not allow the flow of majority charge carriers, that is the free electrons in the N side and the holes in the P side. A very high resistance path is established for the entire circuit, and the current doesn't flow due to the majority charge carriers. But it has been observed that there is a very minute current measured mostly in microamperes. This current is due to the minority carriers. Now, as we know, electrons in the covalent bonds of the semiconductor atoms may absorb sufficient thermal energy to break some of the covalent bonds. Under reverse bias, the thermally generated electrons in P region and the thermally generated holes in the N region are attracted towards the junction, as the present situation acts as forward bias for them, and these minority charge carriers constitute a small current, the reverse current. To summarize it, connecting the negative terminal of the battery to P side and positive to the N side is called reverse biasing. Reverse biasing increases the barrier potential and the width of the potential barrier. The current in this case is only due to minority charge carriers and is in microamperes. There is no current due to the majority charge carriers. Now let us look into the VI characteristics of a PN junction diode. When the external applied voltage is zero, the potential barrier at the junction does not permit current flow. Therefore, the circuit current is zero. When the PN junction is forward biased, the potential barrier gets reduced, and at some forward voltage, the potential barrier is altogether eliminated and the current starts flowing. The potential or the voltage at which this phenomena occurs is called the knee voltage, cut-in voltage, or threshold voltage. The value for knee voltage is 0.7 volt for silicon and 0.3 volt for germanium. The current from this point increases with the increase in forward voltage. The forward characteristic, as you can see, is not a straight line and does not obey the Ohm's law. Therefore, the PN junction is a non-linear conductor of electricity. When the PN junction is reverse biased, potential barrier at the junction is increased. The high junction resistance doesn't allow the current due to majority charge carriers. But in practice, thermally generated minority charge carriers are present and they constitute a very small current in the order of few microamperes. This current is called the reverse saturation current or the leakage current. If the reverse voltage is continuously increased, the potential energy of these electrons, that is the minority electrons, may become high enough to knock out electrons from the semiconductor atoms, thus causing a sudden rise of reverse current and sudden fall of the resistance of the barrier region. The voltage at which this phenomenon occurs is called the breakdown voltage. So we have two situations. In the forward bias, which is shown in the first quadrant, the current non-linearly increases with increase in voltage. In the third quadrant, the reverse characteristics are shown. There is a small reverse saturation current or leakage current due to minority charge carriers, and if a breakdown occurs, there is a sudden surge of current. Now let's look into this breakdown voltage. Breakdown voltage is the minimum reverse voltage at which a PN junction breaks down with sudden rise in reverse current. It can be due to two different conditions. One is the avalanche breakdown. Avalanche breakdown is the breakdown in which the minority electrons passing through the junction acquires high enough velocities to break covalent bonds and generate electron hole pairs. The newly liberated electrons will in turn free other valence electrons. In this way, we get an avalanche of free electrons. Consequently, a large reverse current flows through the junction. If this is not controlled, it may destroy the PN junction as well. Now, there is another way to create this reverse current, and it is called the Zener breakdown. When the PN junction is heavily doped, the reverse current increases very rapidly at certain reverse voltages below 6 volt. At these voltages, the potential at the junction is about 10 to the power of 8 volt per meter. This high magnitude electric field exerts a large force on the valence electrons of the semiconductor atoms, which results in breaking the covalent bonds and producing a large number of electron hole pairs. This results in a huge reverse current. This breakdown is a controlled breakdown and is used in case of voltage stabilizers, where Zener diodes are used as voltage stabilizers. Now let us look into the limiting characteristics of the PN junction. The first characteristic is the maximum forward current. It is the highest instantaneous forward current that a PN junction can conduct without damage to the junction. If the current exceeds this value, the junction may be destroyed due to overheating. Second is the peak inverse voltage. It is the maximum reverse voltage that can be applied to a PN junction without causing any damage to the junction. If it exceeds that value, again the PN junction may be damaged. The peak inversion voltage is of particular importance when we construct rectifiers. Maximum power rating is the maximum power that can be dissipated at the junction without damaging it. It is equal to the product of the junction current and the voltage across the junction. These limiting characteristics are provided in the data sheets of the diodes. Diodes have different kind of applications, and depending upon the applications, different diodes are chosen. We will see one application of the diodes in the next tutorial, that is rectifiers. The books that I use to prepare these tutorials are shown in each slide. I request you to go through these books so that you can have a better understanding of the topic. If you have liked the tutorial, please do like, share and subscribe. Thank you.